Okay, I think we can start. So hello everyone, once again. Welcome on episode 25 of the Warsaw Quantum Computing Group meetings. Today we have a great speaker, Kareem El-Safty from Alexandria Quantum Computing Group. And Kareem will give a lecture titled Yet Another QML Talk. So it will be about quantum machine learning. So just to let you know, this meeting is recorded, so the video recording will be later available on our YouTube channel. And if you have any questions during the lecture, please post your questions on the chat. So there will be a Q&A session at the end. Yeah, but one more important thing is that at the end of this lecture, there will be a survey for people who would like to receive a certificate of attendance. So Przemek Michalewski from the Students Association in Computer Science will send a link on our chat. So if someone is interested, then feel free to just fill it in. Yeah, we would like to thank our partners, our strategic partners who support us, and our honorary patrons who also help us in advertising our meetings. And there will be also some announcements at the end, but I think that now we can give voice to our speaker, to Kareem. So Kareem, if you are ready, the Zoom is yours, so you can start sharing your slides.
Hello, everyone. Can you hear me?
Yes, we can hear you.
That's great. That's great. Thank you so much for your introduction. I really like it and I appreciate it. And thanks everyone for attending this talk. Let me first share my screen. Just a second. Just a second. Can you see my screen right now?
Yes, we can see it.
Okay, I will. So is it clear? I think.
Yeah, it's clear.
There is like a boundary inside, I don't know if everything will be visible for everyone, but let me check. So can you see the Wigner board, the complete Wigner board?
Yes, we can see it.
Okay, great.
Yeah, top right corner.
Okay, great. So first of all, let me introduce myself. I am Kareem El-Safty. I live in Ismailia, Egypt. I have a bachelor in communications and electronics. I am an AI engineer at Division X, which is a startup in a startup company in Egypt, and also a research assistant at Wigner Research Center for Physics in Hungary. I'm also a research member in Alexandria Quantum Computing Group. Currently, I'm doing my master's degree in computer engineering, especially in quantum machine learning. I'm also a Qiskit advocate and certified AI analyst from IPM. I won a national grant for UDAST's AI nano degree like around 3 years ago. I'm also an AI teacher at Information and Technology Institute in Egypt and a certified machine learning specialist from AWS. Like this talk is centered around not only giving the mathematics of quantum machine learning or even the mathematics of classical machine learning. A lot of people before me have given great talks about quantum machine learning and a lot of ideas and everything, but whenever I speak with anyone else, like from the physics community, and ask them about quantum machine learning, I feel like they are like a little bit, separated from what we or from what I'm trying to say. For example, when I talk about regression problems or even semi-supervised problems, anything related to machine learning, but in a bit technical, details, they seem like very, very distressed and also, confused. The same thing happens when I speak with a machine learning engineer and then introduce him to the quantum machine learning world and the potential that we can, or at least we can achieve from applying quantum principles to machine learning. And then again, I find the same confusion and the same stress and the reactions and everything. So uh, what I'm trying to do today is to introduce machine learning for everyone. So the first part, or the first two things in the agenda will be a little bit boring for the machine learning community, and the third and the fourth one will be a little bit, like a little bit boring for physicists. But then 5 and 6 will be the most important thing for everyone in the talk, either you are from a physics background or a machine learning background. So that is what I'm trying to do. I'm trying to give a unified picture of what is actually we have here, or the breakthrough that we are actually living right now. So what is machine learning? Machine learning is simply enough, you are combining some of the computer science algorithms, for example, like trees or graphs or whatever it is, with some statistics. And then you say, here it is, we have a machine learning algorithm. To be more specific, for example, when we multiply some of the weights with some of inputs or some features, and then we apply a transformation to them, and after that we get a probability distribution, and based on that probability distribution we can assign some labels. And here is a machine learning, a very simple machine learning algorithm, which is the logistic regression. I'm sorry, can you mute your microphone? I'm listening, or I'm hearing, a baby screaming. Is that okay? Okay, thank you. So machine learning is just a combination of different subfields, or different, super fields or super categories of fields. For example, like graph theory, or even learning theory itself, with some statistics and some pure mathematics, or even abstract mathematics. And then we have an algorithm that can give us some probabilities, or even some decisions based on the input and the training itself. So that is machine learning in general. I mean, from a theoretical perspective. Machine learning is very popular right now. Everyone can read about machine learning, and even business guys or businessmen and women can actually talk about machine learning applications and how it can transform their companies into a better and better ways. So everyone can learn about neural networks or machine learning in general. Even babies right now can read about machine learning. So it is pretty standard, pretty common, and we have a unified way of introducing machine learning and neural networks to everyone. That is something that cannot we cannot do, for example, for quantum physics, or even for quantum machine learning. It's a little bit hard, and you cannot grasp it very well. At least quantum physics has right now like a standard way in the university textbooks. But again, if you want to introduce quantum physics, for example, to a business guy, then it will be a cumbersome to agree on the terms that you should use and how you can apply them, or not just apply them, but use them for a special use case for each one. So it is not that easy to have like a normalized way to introduce such a topic like quantum computing, or even quantum physics, like we do in neural networks or machine learning in general. Machine learning is very popular, and it is gaining more popularity because of the following. We have a paper, and then the authors can have like a GitHub link or a GitHub repository. And after that, we have like different frameworks for machine learning, and we have like TensorFlow, PyTorch, MixNet, and before them there was Theano, and there are another like brand new frameworks, for example, like JAX. So for example, I like TensorFlow, me, myself, and I. So if I found if I find a paper that is actually implemented like in a nice way and also on GitHub and it is written in TensorFlow, then everything runs perfectly even on my system. I don't have to re-modify the environment of my system to run everything. Then that's great. I will start implementing it and I will start debugging it, and the most important thing, I can even develop it or apply it to another problem. So that is what makes machine learning very accessible to everyone. Just easy coding, and easily accessible, and we have like a pretty standard way of presenting the ideas and also presenting the results. An important thing that at least the physics community should differentiate or understand is that we have three main terminologies that unfortunately we use them interchangeably. For example, artificial intelligence or AI, machine learning, and deep learning. Artificial intelligence is a very broad thing. We have a lot of subcategories that we can study, and like one can at least spend a lifetime only studying optimization problems, and that's it. And that is like a very subfield in AI in general, or NLP, or computer vision, or speech recognition. So there are a lot of things in AI, even supply chain analytics, or even you know uh, some part of game theory, or at least let's say that, for example, like playing Go or chess using AI. Uh, this is another way of spending like a very big deal of time only in the AI section. And then we have the machine learning section, or the machine learning inner circle. Machine learning, as I said, it combines a lot of fields, and it is actually a subfield of AI. Machine learning can be used in computer vision, it can be used in NLP, it can be used in optimization problems, and even it inherits a lot of things from the optimization field in general. The deep learning part, or the most inner circle of those three things, the deep learning one is a subfield from machine learning, which only focuses on neural networks, and that's it. So it only focuses on neural network, whatever the application or the type of learning that you are trying to do. So it only focuses on neural network. But machine learning, it focuses a lot on, for example, like support vector machines, random forests, logistic regression, k-nearest neighbor. So there are a lot of algorithms, but in deep learning, you have only neural networks and its variants. So we have a lot of variants in neural networks, but in general, deep learning is only specified for neural networks. A general overview for machine learning is that we have three types of learnings. We have supervised one, we have reinforcement one, and we have the unsupervised learning. Let's break them down a little bit, and also in an easy way. If you want to introduce machine learning for a toddler, for example, not just a toddler, for example, like a 5-year or 6-year-old boy or a girl, you can tell him or tell her that whenever you do something wrong, I will punish you. But whenever you avoid that wrong or that mistake, I will give you some reward, or for example, buy an ice cream, or anything. You are trying to condition her behavior, and based on that behavior, you will give her like a reward or a negative reward, whatever that reward is. So that is reinforcement learning. There is like an agent, and that agent is doing some behaviors or doing some actions, and based on those actions, you will penalize it, and you can give him some bonuses, or you can punish that agent. And that is simply enough the reinforcement learning section. The supervised learning one, simply like when your baby is trying to learn the surroundings or its environment. So we have, for example, you can introduce him to the garden, and you can say that, okay, we have a tree, and that is a tree. And after that, it is automatically in his or her brain, it will start to generalize very well over other examples, and whatever the next tree he or she will see, okay, it will say that this is a tree. So that is pretty common, and the human brain can easily do that. So the supervised learning thing here is that you give your baby an example, and also that example is labeled, or we already know what type of this example it is. Or for example, we can say that this is its label. Okay, so we have a sample and we have the label. The sample is that there is an image, for example, and that image has a tree, and the tree is the label. So that is supervised learning. Unsupervised learning, simply, we don't know the labels, but we have a lot of samples, and we are trying to find the pattern inside these samples. We can easily enough, give a very, very simple example for this. Like if we have like a gray puzzle, or like a lot of pieces, and then we are trying to combine them together so that at least we can have like a pattern, or we can gather it in a way that we can we at least have like a good shape of something, or that pattern can be understandable, or we can extract some information from these pieces. So that is, for example, like the unsupervised learning. So those are the three kinds of learning. Of course, there are another how can I say it, another types of learning. For example, the semi-supervised learning. There is single shot learning and a lot of advanced ones, but those are the three main ones, and we can derive the rest of the learning types from these three. Okay. This is the most important thing here. Let me make it. So yeah, I think it is very well. Um, can you please mute your mic? Yeah, thank you. So we have three steps in each machine learning pipeline, or in whatever the model you are trying to create. You will always go through those three steps. You cannot avoid them, and that is like the standard, or that is your own pipeline. You cannot change it, and it is pretty common in many companies to follow those three steps. The first step is that we have a problem. Okay, any machine learning algorithm, or any machine learning job starts with a problem. We have a business problem, and we should define it very well, and based on that definition we start to collect some data. So we have like some data storage locations, and after that we do some ingestion on this data so that we can stream it into apply a pipeline of data preparation. So data preparation contains a lot, or there are many pre-processing steps that we can do depending on data types. And for example, images, we will, like the standard way of dealing with images is normalizing them between you just divide by 255 so that everything is between 0 and 1. That is like the most basic one. But lately, if you have like an RGB image or a colorful image, then each channel is standardized by its mean and standard deviation. So that is another way, for example, on data preparation. And after finishing the data preparation, and in many situations, you will have some missing features, so that you should do some imputation on those features. And after that, you go to the next step, and that next step is the model training and building itself. So each machine learning algorithm has a lot of hyperparameters to be tuned. For example, in the support vector machine, especially enough the kernelized one, you will have a lot of parameters to be tuned. For example, there's something called C, the regularizer. And there is something called gamma, which is, for example, if you are dealing with the radial basis function, then you should carefully choose the gamma parameter. And after that, you should choose if you would like to shrink the space of the features or not. You should also check if you would like to, if you are dealing with a polynomial kernel, then you should also choose if you would like to have it like a second order polynomial or third or fourth or fifth. So it depends a lot on the distribution of your data. So that is hyperparameter tuning. And after that, you do some validation on your training data and also your testing data. And after that, you go to the server and then you deploy the model. And I know that this is not very relevant to our talk, but at least, you know, after the deployment itself, the life cycle does not end. We still have a lot of things to do actually. For example, like you should monitor your model so that there is no drifting in the output. For example, after for like 3 or 4 months, the model may or may not, depending on the input, may start to produce some, you know, bad decisions or bad outputs. So that is, you know, data drifting or model drifting, and you should carefully, you know, retrain your model on the new input or the new data that comes to the pipeline, and you should refine your model over time. So that is another situation and another story. But right now, we only have the deployment and prediction, and that's it. So that is the whole typical machine learning pipeline that right now each company on the planet Earth actually follows this pipeline, and we should think at least when like in a few seconds or in a few minutes, you know, when we talk about quantum machine learning, we should think about, you know, that pipeline. Where should we actually quantize it? For example, in the models itself, should we only change the model instead of like a classical model? We should do like a quantum model and that's it, or the data preparation, should we do any quantum operations on this? Or in the deployment and the prediction, should we, for example, use quantum computing in that part for only security or for enhancing machine learning? So there are a lot of things that we can use quantum computing for in the pipeline, a lot of things. But anyway, let's continue. This is a very simple example of a machine learning algorithm. That is the logistic regression. We have some inputs or some features. For example, we have like 2 features here. Okay, and then we have two weights, W1 and W2, and we have a pies. And then that is the main equation or the learning equation that we have here. Simply enough, we multiply x1 by w1, and then we do the summation. And after doing that, we add the bias. And then we do a very simple transformation, which is a sigmoid function. Okay, so sigma z is simply enough a sigmoid function. And then the output would be a probability between 0 and 1. And based on that probability, as I have said before, we have like, for example, like the tree example, we have a label. So if we can, for example, if we are classifying, you know, cats and dogs, cats can have like 1 and a label 1, and dogs can have a label of 0. And the loss function here is something called the binary cross entropy. Okay, and as you can see here is that if the label is 0, then that whole term will vanish, and the only thing that we will have here is this one. So if it is a 0, okay, and if it is a 1, then sorry, just a second. Just a second. Sorry about this. So in the binary cross entropy, the outputs should be like a probability between 0 and 1, and the labels should only be 0 and 1, and that's it. And based on 1 or a 0, you will try to minimize that cost function as much as possible, so that you can have like a good prediction model, or a good model that can output like some great predictions, and that's it. That is the whole thing about that example. Another thing that we should also mention here is that we are using something called backpropagation, and backpropagation is simply enough. You are differentiating the loss function, okay, along the way with the weights and the inputs, and that's it. And based on that differentiation, you are starting to do the optimization loop for logistic regression. And based on that optimization, you will update the W1, W2, or the weights, and also the bias. And based on that update, your algorithm will converge, so that at least at the end, you will have like a good, separation between the data points. So as I said before, we have like two types of data, like cats and dogs, or in this case some points, red points and blue points, and you are trying to find a hyperplane or a separation between those 2 points, or these points. So a logistic regression can easily enough find that separation based on the backpropagation step that you are doing, and using the binary cross entropy function. What I'm trying to give by that example is the following. We could have, instead of using the binary cross entropy, we could have used something called the mean squared error function. Okay, and in that case, it would be wise to have the labels to be, instead of 0 and 1, to be 1 and -1. Why I'm saying that? It would be better to have like a good separation between the 1 and the -1. 1 and -1, it's like a huge margin, and based on that huge margin, the mean squared error will perform better. So we should think about machine learning in general as or from like an abstraction way. We should think about machine learning as, a big black box. Okay, and that black box is, we have some inputs and then we have some outputs, and we are trying to find a way so that we can map the inputs to the outputs, and that's it. And based on the outputs, we can update the parameters inside that black box. So depending on the loss function, the whole optimization procedure can change dramatically, and also the conversions can also change dramatically. And even if we do any pre-processing over the features, then we can make the classification problem extremely easy, or it can be very hard. So it depends a lot on the type of input or the shape of your input, and also the shape of your output. Is it only probability? Is it like a continuous distribution, or whatever the shape of your output? So that is an important, an important perspective that we should look at when we are trying to create new algorithms in machine learning in general. So I think if there is any questions regarding this part of machine learning, is there any, or are there any questions that that anyone would like to ask?
I don't see any questions on chat, so I think we can go on.
Okay, great. So, introduction to quantum computing. So, anyone here from a physics background will find it a bit boring right now, but for the machine learning community, or anyone from any other background, you can think of quantum computing instead of those crazy ideas about entanglement and superposition and like very complicated equations. You can think of it as a new computational paradigm. Let me explain it a little bit more. Understand quantum physics. So think of this as the following. If we have like uh, the addition operation between 3 and 4 simply enough is 7. That is pretty clear and pretty straightforward. But in some situations, we can say that 3 plus 4 is only 0. How can we do something like this? Or is it even possible? Yes, it is possible if we consider that only the numbers that we have starts from 0 up until 6. So we have only 7 numbers. And if you would like to, do the addition between 3 and 4, then you will reach 6. And after that, we don't have a 7 in this group of numbers. We only have 0 up until 6. So you will have to go again to 0. So uh, the same thing actually also happens in our computers. Our computers only understands like a very, very simple voltage pulse. Okay, and that based on that voltage pulse, it can either be a 0 or a 1, and that's it. And I'm talking about, the transistor level itself. So if we have a voltage pulse can be represented as a 1, and no voltage pulse can be represented as a 0. So if we have like a group of 2 numbers, and those 2 numbers are only 0 and 1, then 1 plus 1 is simply enough as 0. I know that there is a carry, and we should like pay a careful attention to it, and the whole logic arrays inside our CPUs are also giving much attention about this. But what I'm trying to tell you here is that the computer itself, or the people who actually invented, the Boolean algebra itself, are thinking of everything, or representing all the data in our normal lives. For example, images, voice, videos, or any other type of data. We only represent them into zeros and ones. Quantum physics also actually represents everything in zeros and ones, but it gives us much freedom in saying that, okay, we can have some probability that that would be 0, we can have some probability that this would be 1. There's also another thing that we can say, we can also represent it in a very, generic way, because we can also add some complex numbers to the representation itself. So if we have like a single bit as a classical, computational unit, we have like in quantum computing, we have something called a qubit, and the qubit can be actually complex. It can be real. It contains. It can be in something called superposition, because as I have said before, we have some probability it could be in a 0 state or a 1 state. So it depends a lot. Uh, there is also another, computational paradigm inside even quantum physics itself, which is called the continuous variable model, where you don't only have 0 and 1, but you can actually go from 0 up until infinity, and that is the continuous variable model, and it can be represented in 2 ways. One of these ways are called the Fock representation, and the other one is called the Gaussian representation. And those are very similar to each other, except for that in the Fock backend, or I mean the Fock representation, you can apply some higher order Hamiltonians. And what I mean by higher order Hamiltonians, you can have like a cubic or quadric Hamiltonians, or even higher, like 6th or 7th. So it depends on the Hamiltonian that you have. So that is the beautiful thing, about quantum computing. It gives you a lot of freedom to represent more information, but instead of using a lot of bits, you are using a very few qubits to represent like a huge pile of information. And that is something that you don't usually have in the classical computation, or the classical paradigm that we are used to, and we don't even think about it when we are, when we are taught about computers and how they work, and logic gates and everything. Okay, we have zeros and ones, and that is pretty easy, and we can do the Boolean addition, or the Boolean algebra in general. But we don't think of it as, okay, what if I have like another representation, if I have like 0, 1, and 2, or if I have like something in between, can we have some probabilities in between? We don't think of it like in this way in the university, or even in high school. But quantum physics simply enough, gives you the opportunity to have some probabilities between 0 and 1, and also it gives you the ability to have complex representation of information. So that is the beautiful thing about using quantum physics as a new computational paradigm. Easily enough, without going into much details, a qubit, a qubit can easily be represented as the following. We have here something called a kit, and that kit, the mathematical representation of a kit is very simply a column vector, and that vector for the 0 it is 1 0, and for 1 it is 0 1. So it is a column vector, and as you can see here, we have some representation for the probabilities depicted as cosine theta over 2 and sine theta over 2. And we have here like a phase, and that is a global phase. And a qubit can be easily enough represented by something called a Planck sphere. So you can rotate your qubit around that Planck sphere as you wish. You can have it on the x-axis, the y-axis, or the z-axis. And that is, the 0 is always depicted here above the Planck sphere itself, and the 1 is always down. So that is the representation that you can do, and by that representation, perhaps you can start thinking, if you are thinking about, for example, about embedding or if you have like only a single qubit and you have like 3 features, okay, and you would like to put those 3 features inside that qubit or that quantum computer, and that quantum computer only has only 3 qubits. I mean, only a single qubit. Then that single qubit, if we take that representation and then expand it into the spherical representation, then we would have, for example, the theta and the phi and also the lambda, and based on those 3 angles, we can embed 3 features inside a single qubit, and that is something that is actually very how can I say it? It has a lot of capacity to represent information against the classical bit that can only be a 0 or a 1 in a certain condition, and that's it. But as you can see that here in the qubit, you can actually put a lot of information and still you can do a lot of things with it. So that is something that is what makes quantum computing very interesting in general. Those are like the standard gates in quantum computing. Of course, there are a lot of other gates like the rotational X or Y or Z, or even like the generalized rotation, as I have said before here when I give you an example about embedding 3 features inside a single qubit. Okay, let me go through them very quickly. So an X gate, simply enough, it makes a 0 1, and the 1 it makes it a 0. The Z gate simply it doesn't affect the 0 state, but it affects the 1 state by a phase, and the phase is -1. The Hadamard gate puts the qubit in a superposition way. The T gate is just a phase. There's something called a C node or a control gate, and based on that control gate, we can do a lot of stuff and a lot of the magic. Like, for example, entanglement. We can make 2 qubits entangled by easily applying a Hadamard to the first qubit, and then a C node between them, and based on that controlled C node, then we will have an entanglement. And there is something called swap. For example, if you have like some values in the upper qubit, and you want to exchange the values between 2 qubits, so that the values in the upper qubit will be in the lower and vice versa. So those are like the very popular gates in quantum computing. There are a lot of things, for example, like the Toffoli gate. We also have like the controlled rotation or controlled Z. So there are a lot of so to be more specific, the X and Z and H and the Y gate is not here. can be easily enough combined with the C node, and you can have any gate that you can imagine, and also you can do any kind of computation. So it is a universal gate set that you can use to do any type of computation. So again, as I have talked before, let's talk about some abstraction about machine learning and also quantum machine learning. I have said before that we have some data, and this data we are doing some pre-processing on it, and then we give it to the model. Okay, for a quantum computer, unfortunately, up until now, quantum computers are like in a very restricted area, and that area is very special. It should be like very cool, like near the absolute the absolute temperature of 0 Kelvin. So it is actually extremely cold, even colder than the outer space, and it should also be isolated from any type of noise, even the noise from the controlling wires itself. So it should also be isolated from this, and you only interact with it. For example, in the case of IPM, you can only interact with it by giving it some instructions, and you are waiting for the output from the quantum computer. So how can we get that that machine learning pipeline? How can we actually apply it in the quantum case, or in the quantum machine learning case? So the first thing is we should first on a classical computer, we should do some pre-processing on our data. For example, if you have some missing features, then you should do some imputation. If you have some problems with the scaling of your data, and some features are very small and some features are extremely high, like for example, you're talking about 1 up until 5, and the other feature is like 10,000s or even millions, then you should do some rescaling so that everything is at least comparable, and you can at least verify the visualization of your data set. And after that, you should think about how I can embed, or how can I insert those features inside the quantum circuit itself. So in this situation, there was like a suggestion from people in IBM, and in like I think we can say 3 years from now. Yeah, I mean 3 years ago, they introduced something called Pauli feature maps, and those maps uses something called control or a ZZ interaction. A ZZ interaction is simply something like here is a C node and another C node, and then there is a rotation around the Z axis, and that is the ZZ. Okay, we can have other other Pauli feature maps. We can have like the X or the Y, or we can have some combinations between them. So it is completely free for you to change the feature map itself, or the embedding itself that you are trying to do. And after encoding your data, so this part here is just you are encoding your data inside the quantum circuit. Then here you will have like some gates. For example, here the U or the U3 in some textbooks is just a general rotation gate around the block sphere. So before I have told you that we can embed 3 features in a single, or we can have 3 parameters for a single qubit or for a single gate, and those parameters can actually rotate the qubit around the block sphere. So here we have the U gates, so we can apply it to 3 qubits, and then we can increase the complexity of the circuit by introducing some entanglement over here, and those gates are variationally optimized over and over and over by something called computing the gradients. So yes, we can actually compute the gradients or the derivatives of this quantum circuit, as we have done for the logistic regression there have been a lot of proposals of how to compute the gradients, and currently the most famous one is the parameter shift rule, and that rule can easily, it is, quantum hardware friendly, and it proved to be very successful in many situations. And based on those gradients, we can update the weights here. And based on them, we will have some different distributions or different outputs. And those outputs can be fed into any post-processing, any post-processing function. And based on the function, we can have some boundary decision, and that boundary decision will give us like a label of 1 or 0 in the case of, for example, like we are classifying cats and dogs. Okay. Or we can have like multi-labels, so we can have like the analytic values from each qubit, and then we can feed it into a softmax layer. Softmax layer simply it gives us a probability between 0 and 1, and based on those probabilities, we can have something called the cross entropy function, or the multi-class cross entropy function, and based on it, we can calculate the loss, and then we will have like a good quantum machine learning model. And that is like the whole pipeline. But inside the quantum computer, we should do some data encoding, and we should carefully choose the data encoding so that we make it easier for the variational circuit to be actually operating very well. And let me elaborate more on how it can be like hard one or an easy one. For example, most of the gates, or all of the gates actually, are just, we or the values inside the gates here in the ZZ, for example, the ZZ are ranges from 0 to 2 pi. Okay. And if your inputs are extremely small, okay, then most of the features or most of the samples will be the same. So it will be very hard for an embedding scheme to an embedding scheme inside quantum computing, or inside quantum machine learning model. It will be very hard for it to differentiate between different samples, and that's a problem. Or it could be, for example, like very high, and because of the periodicity of the Euler angles or the radians, then it will be the same. So you should pay careful attention to the way that you do the pre-processing, and also to the type of gates that you are using to embed your features. In some situations, some people do not like to start with a superposition. They simply enough apply rotational gates directly. So it also depends on the performance. There is no there is no general rule here. And by the way, in machine learning, because of I know that because of a lot of experiments and a lot of papers, we have some standards that we actually follow, but at the end we can create new standards, or we can create a new ways of pre-processing the data depending on the situation and the business problem. But at the end, we have some standards in machine learning or classical machine learning, but in quantum computing, we do not know like a general rule or what is best. For example, like speech data, how should I encode it? Or for example, for images, how should I encode it? So there are a lot of a lot of ways to encode your data, and perhaps it might give you better results or not. Regarding the variational part, or the variational ansatz itself, if the encoding is very well, and it actually makes it easier for the variational ansatz to classify it very well, or the distribution itself is doing great, then we do not have to increase the complexity of this part, or we even don't have to repeat the whole this. So for example, in neural networks, this is considered to be like a single layer. Okay. So we do not have to repeat it over and over again. And this means the following. We have a huge reduction in the depth of the quantum circuit. And that reflects, and that is reflected on, the healthy output from the quantum system itself. If you have like a very deep circuit and a very wide one, like you have like a lot of qubits and you have like many gates to handle, then because of the noisy nature of the current quantum hardware, then the output would be simply enough, white noise or a Gaussian noise. There is nothing that you can actually extract from the quantum system itself, and that is a disaster for you. So if you have like a very efficient way of encoding your data using limited, very limited, types of CNOTs or whatever the type of encoding your data, and also if you have like a very efficient variational ansatz, and that ansatz is very small and it does not require a lot of 2 qubit gates, whatever the 2 qubit gate that you are using, controlled rotation, control Z or control Y, whatever the two qubit gate that you're using, then you are giving us like a huge a huge improvement in the quantum machine learning community. So using less and less of gates and less of qubits is a good thing. But in some situations, complexity is the only solution to find a better decision boundary for yourself. So that is the idea of quantum machine learning. You just encode your data, and then you have some variational ansatz, and then you do the measurement, and based on that measurement, whatever the type of the measurement that you are dealing with. For the case of IPM, you will have zeros and ones. In some situations, you can convert the zeros and ones into analytic values, so it will be like a continuous output between -1 and 1. In the case of, if you are, for example, measuring the Z axis, then the eigenvalues of the Z matrix is 1 and -1. So whatever the output, it will always be bounded between 1 and -1. But if you have like a certain type of Hamiltonian, for example, if you have like a regression problem, and that regression problem requires like an output between 1 and 10 or -5 and 25, then you should have some sort of Hamiltonian, and that Hamiltonian should, I mean, the upper and lower values, or the max and minimum value of the eigenvalues, should be like cover the whole range of response of the response variable, or the target variable of the regression problem that you're dealing with. So anyway, it depends a lot on the problem, or the formulation of the problem, and the formulation of the loss function, and that's it. That is the whole abstraction of any quantum machine learning problem that you will see, even in any paper that comes. Like, at least from my understanding, and please double check or triple check my understanding also on my claim. Anything is only, or any paper in quantum machine learning is simply, you are trying to do some data encoding, and you are trying to choose the best data encoding for your own data set, and that's it. That is not like a universal one. Okay, and then you do some variational ansatz, and after that you do some measurements, and based on that measurement you will define your loss function, and that's it. So that is the whole pipeline. Another way of thinking about, but before going into this one, is there any question regarding this simple abstraction of quantum machine learning?
Yes, Kareem. In fact, there is one question from Maciej. The question is, are we talking about using quantum computer to implement some machine learning model? So quantum computer version of neural network, or just to implement quantum version of backpropagation algorithm?
No, right now I'm talking about implementing a quantum machine learning algorithm, not specifically quantum backpropagation.
Okay.
Okay. Is it a good answer, or is it still not obvious for you?
Maciej replied that yes, it's a good answer.
Okay, great. Okay, let's go to the other thing here. So, in machine learning, by the way, in classical machine learning, we still have like a very simple problem, and the problem is that what if that our data is not linearly separable? Okay, so for example, here we have linearly separable data. It is very easy to be separated by a very simple straight line, or even if we have like many features and those features can be separated easily, then it would be like a hyperplane, and that is easy. But in this situation, then we cannot have like a single straight line to classify our data, or even this one, or this one. So for example, here, this is also not like like uh, how I can. This is not linearly separable at all. This is the only case that we can do it with a very simple straight line problem. Okay, just a second. My cats are fighting. Just a second. I'm sorry. Hello, hello again. I'm sorry about this, but my cats were fighting furiously. I'm sorry about this.
Okay.
Anyway, anyway, uh, yes, the kernels. So uh, there is a very famous algorithm, which is the support vector machine, and the support vector machine comes with a very nice trick, which is called kernels. And the kernels are simply enough a function that you can apply to, or a transformation that you can apply to your data. And based on the output, you can classify your data very easily without the need of any, any crazy or complicated stuff in the case, like in the case of neural networks. So we have like three popular kernels: the polynomial one, and the radial basis function, and there is something called the tanh, or the sigmoid. In some situations, they call it a sigmoid. Okay. And the tanh is, of course, between 1 and -1, but the sigmoid is simply enough between 0 and 1. So in some situations, they used those two items interchangeably. So do not get confused about this. We can have the same thing in quantum computers. We can actually encode our data using whatever the type of encoding. For example, we can have something called angle embedding or amplitude embedding, or using the Pauli feature maps like in the IPM paper. And then we can apply the same transformation, but the conjugate transpose of that of those values. And then we project the output or the probability distributions on the zeros, or the zero state. And the output will always be a positive, okay, and it will be between 0 and 1, and that's it. So we can actually create something called a Gram-Schmidt matrix, as we actually do in classical kernels. Okay, and instead of using those classical kernels, we can use quantum kernels, so that we can compute the similarities and everything. And then the matrix that we will actually compute, we can use this matrix to be fed to the classical SVM. And then we have a hybrid approach of using quantum and classical algorithms together. So that is like a very popular one, and it is a little bit it is achievable, and it has been demonstrated in a lot of papers, and we will also see it with each other. But let me show you what I mean by the complex conjugate, and the same thing. So as I have seen you, or as I have, showed you before, that, for example, we have like a quantum circuit, okay, and that quantum circuit can be initialized with Hadamard, and then we have something here like this is like the Pauli feature map that I talked about. For example, here in the X, we can have it like in the Z, or whatever the type of the rotation that we would like. and we can repeat that. And after finishing it, we will, if we like repeat it like 3 to 4 times, then we will do the same thing, but the inverse of it, or the the complex the conjugate transpose of it, or the dagger representation, and that's it. And based on the output, okay, we can have a matrix, and that matrix is always positive semi-definite, or simply enough the Gram-Schmidt matrix for the SVM, and that is pretty much easy. Or, as I have shown you also before, instead of doing this, or the quantum kernel one, we can simply enough embed our data and then do some variational ansatz, and then we can have the outputs. So we have two approaches here, the quantum kernel one, and by the way, we can simply enough compute the Gram-Schmidt matrix and have the similarity output, and based on that similarity, we can actually say that, okay, this sample belongs to that one, and that sample belongs to that one, and that's it. Or we can do it like in a neural network way, or in that case, a quantum neural network way. So let's find. Is it okay, or do I have time to have some examples, or to show you some examples, or not?
Yes, yes, we still have time.
Okay. How much? I'm sorry.
How much time do you need?
Well, it depends on on the audience and you.
So I think that you can take half an hour or so.
Oh, okay, okay. So let's, for example, we have here actually 3 examples: the Qiskit one, and also a penny lane one, and also an example that I have created like around 3 years ago, or I think, yeah, about 3 years ago. So let's go to that one. So can you see the my Google Colab, or
Yes, we can see it.
the Google Colab thing? I mean the Jupyter Notebook.
Yes, we can see it in collab.
Okay, okay, that's great. So 3 years ago, there was a quantum machine learning course by Professor Peter Wittig, may God rest his soul, and he talked about quantum kernels and how we can use them to do hybrid quantum classical machine learning, or even we can use it like in a pure quantum way instead of combining it with a classical one. Okay. So in this situation, there is something called squeezing kernel. And that squeezing kernel is something from the continuous variable model. I'm sorry, just a second. Just a second, I'm sorry. Okay, I'm back. So yes, the squeezing kernel. The squeezing kernel has been presented by Maria Scholz and Nathan Killoran, like also around 3 years ago, and it was a very interesting paper because they have introduced like a Gaussian kernel, not a Gaussian like the radial basis one, but from the Gaussian, the Gaussian system, or the continuous variable system, but in a Gaussian representation, and also the Fock representation, they said that we can use the squeezing gate to embed the classical features, and then we can compute the similarities between in the case of the standard quantum computing thing, we call it a qubit, but in the continuous variable model we call it a quantum mode, or a Q mode. Okay, so if we have like 2 features and then we have like 2 Q modes, then we can compute the similarities based on that squeezing gate. And to think of the squeezing gate, we can represent it very naively by the following example. So of course, many of us have watched Tom and Jerry, and in some situation, Tom's actually Tom is simply enough is hit by something, and based on that hitting, his body starts to be flattened, and if you look at his face, you will find it very wide, but if you look at his side, you will find it very pointy and very thin. So that is simply enough the squeezing. You are squeezing one side and then you are expanding the one, or you are punching something and anti-punching on the other side. That is simply enough the squeezing. And the same thing actually happens for for our case, we are squeezing a direction, for example, like the X direction, and we are anti-squeezing the P direction or the momentum in that case. So this is the squeezing kernel, okay, but computed classically. So this is a tractable one. There's no like huge quantum advantage or anything. No, this is completely, computed classically, and there's no like real quantum advantage in that notebook. So I'm not claiming that I'm doing like some great magic, okay. And based on the kernel, we will compute something called the Graham matrix or the Graham-Schmidt matrix. And based on that matrix, uh, let me run the notebook. I think it will be nice. Yes, run anyway. Just a second. So if we have like a very simple example of those two vectors, okay, so those two vectors or those two samples, it will create a 2x2 matrix, and here is the amplitude of the squeezing or the magnitude of the squeezing. And you should know that by increasing that magnitude or the amplitude of the squeezing, you will find that here the diagonal is extremely the same. I mean, it is like the largest value, and the off-diagonal elements are very close to 0. Okay, so the same thing actually applies if you are computing the polynomial kernel or the Gaussian kernel. I mean, the radial basis one or the sigmoid, so whatever the kernel that you are trying to do, it will also produce the same output. Okay, so another example, for example, here. So the data preparation, let's make it a little bit, noisy. So as you can see, here we have a data set, and then we split the data set. So that is the basic, the data preparation or the pipeline that we are talking about. Then we are preparing the data set, and then we do some transformation on the data itself. Okay, let's make it a little bit more hard, factor of like 2. Okay, anyway, and then we should compute the Graham matrix for the training data and also the testing data. And we have a hyperparameter here, and that hyperparameter is the amplitude of the amplitude of the squeezing. It will take some time. Okay. And here you can plot, the Graham matrix using only, some sort of, you can actually show some, some columns of the Graham matrix, or you can actually plot the matrix itself. And you can, there is a command line that you can actually plot the matrix itself. I forgot to do that one. I'm sorry about this, but we will actually see it in the Qiskit example. And then we have here a support vector classification, class, and then we here say that the kernel is already pre-computed, okay, and then I feed the Graham matrix of the training data, and I give it, I'm giving it the training label, okay, or the response variable, and then here I'm computing the training score, and then I'm doing some cross validation to make sure that it's not overfitting. And then I'm testing it with the Graham matrix for the testing data. So the training score is 1, the validation is also 1, and testing accuracy is 1. And that is the let's wait for the yeah. As you can see, here's the decision boundary of the data set. Okay, we can clearly enough, classify, the blue dots and the red dots very, very efficiently, and it is working. So instead of having the kernel that way, computing the kernel that way, I mean, in a classical way, we can actually use here the penny lane example. I think have can you see my my new tab? I mean the kernel one.
Yes.
Okay, so in this
Yes.
example, okay, so in this example, they are here. They are using something called the iris dataset. So this is one of like the benchmarking datasets, and it is very old, and they are following, you know, the here this one here the kernel approach, which is you are embedding the data using like some sort of a circuit, and then you are uncomputing it using the conjugate of that one. And after that, you are projecting it over the zeros. You can do that easily but in PennyLane by simply enough, you know, there is a template inside PennyLane that says angle embedding. And I think the default embedding is the X rotation. And after that, you do the inverse of the embedding itself. And then you calculate the expectation values of the projector, and the projector here is simply enough the zero or how can I say it, the Hermitian matrix of the zero operator, and that's it. That is your kernel, and based on that you can do the same thing, you know, the prediction, and you can compute the scores and all of these stuff. So that is like pretty straightforward. The same thing can also be applied for the Qiskit situation. So here is the quantum enhanced support vector machine. Okay, they are using here the ZZ feature map, but in the library here, if you like dig deeper in the documentation, you will find that there are a lot of things, and instead of the ZZ feature map, you can also, you know, feed your own feature map. You can create your own feature map that is completely achievable, and you can do it easily. One of like the standard datasets that they actually use to benchmark their idea of the feature map is something called the ad hoc dataset, as you can see. And by the way, do not be that astonished that a quantum computer can actually, you know, find the patterns of, you know, the blue dots and the orange ones, and that is like a very hard task. You know, it can be easily achieved, but if you think of it like in a 3D way, you know, in a 3D dimension, then you can easily enough, you know, the blue dots are like in the upper space, and the orange dots are in the lower space, and then a very simple hyperplane can do it, and that's it. So it's not that hard. It's not a very hard data set, but at least it is one of the benchmarking data sets that IBM depends on it for their feature map paper. And that is the Gram-Schmidt matrix, or the kernel matrix itself. By the way, if we plotted the same matrix here, for example, in our situation, okay, if we plotted the same matrix, okay, I forgot to, I'm sorry about this, but I forgot to plot the matrix as in this case. You will find that most of, you know, the diagonals are extremely close to one, okay, and the rest is very, you know, is very low, and that is the typical a typical way of the Gram-Schmidt matrix, and it is always positive, okay, so that one of its properties is positive semi-definite matrix. And that's it. That is the idea behind, you know, quantum kernels, and that is the three examples that I wanted to show you very quickly. But of course, I will give the slides to Mr. Bavel, and you can check the notebooks whenever you want. One use case, like quickly, and it's like a little bit of self-publicity. Last year in January, so like a year ago, let me try to reduce this size a little bit. So I think, yeah. So uh, uh, I have written a paper with my senior colleague about, you know, trying to classify, no, not only not just classification, it was about regression, you know, doing classical and quantum regression for an organic photodiode. So the dataset was simply the following. We had two features, and those two features are the voltages. So it ranges from -3 up until +3. And the other feature is the intensity of the light that actually hit the organic photodiode itself. And the output or the response variable or the label, for example, is the current. So the problem here is that I'm trying to, predict the current, and that's it, based on, the feature of the voltage and the features of the intensity. The intensity values were ranging from starting from 0 up until 80. And as I said before, the voltage between positive and -3. So most of the papers that actually came before our paper, they were only doing like a fitting problem, and that's it. They are trying to fit, the output of a photodiode, and the output of a photodiode is very similar to, a sigmoid function or a tangent function, and that's it. But I told them that let's treat it differently. Let's do it in a regression way, so that at least when we do the experiments, it is a pretty much expensive, to go from 0 up until 10, and then to 20, and then to 30, 35, and then 40. So there are like the in-between values between each level of intensity, and repeating the experimentation is not, it is very expensive in many situations. So I told him, let's create a model, and that model I will try to make it very generalized, so that we do not have to, repeat the whole, experiment over and over again for a specific intensity. He was skeptical about this, but at the end, I have done the very same thing, about I have a data set, and then I have done the splitting, and after that I prepared the data. So I made sure that the ranges of the voltage and also the intensity are very, very close to each other, and also I used different approaches, and I used 4 approaches: the K nearest neighbor, something called TPOT, and something called the artificial neural network, or sample feed forward neural network, and the quantum neural network. Let me explain to you what I mean about usability, and why the QNN did not, for example, produce like the best, the best results. First of all, let's be clear about something. This is a very simple data set. It's not that hard. I only have 2 features, and you can clearly see that when the voltage is very low, then the current will be very low, and it will also be negative. So if you have a negative voltage, then that is completely, completely right to have a negative current, and that is like a linear relationship between the voltage and the current. But there is another, like nonlinear relation between the intensity and the current itself, and you can see it here by looking at, the bottleneck of each curve, and also, the distribution of each, of each value. And what I'm trying to say, the distribution here, for example, the intensity of 80, you can see that here, the difference between each value. For example, if you have like the voltage is 3, then the current will be very, very high, okay? But in the case of the intensity of 0, then the current will not be as much high as the intensity of 80. And that is something that is like non-linearly, correlating the intensity with the current itself. So that is my data set, and that is the only thing that I should be, I should at least be careful about when I try to choose the model. And by choosing the model is that it's not reasonable to choose a linear model for this regression problem, because the intensity is not linearly correlated with the current itself. So the KNN model is not a linear model, and it's not parametric. It's a non-parametric model, and that is easily can be proved, and it has been proven in many papers and many textbooks, and it is very easy to be trained. So when I say that the training accuracy is 0, that is completely logical for a KNN, because the training phase of a KNN, it just saves the matrix as it is. And in the testing, it tries to find, the, the nearest samples, and then it calculates the distance, and based on that distance, it assigns the label. And that is the KNN, that is the KNN model. And the usability here, I mean, if you want to develop that algorithm by yourself, then for a machine learning for a machine learning practitioner, then it is pretty straightforward. You have a data set, and then you apply some transformation to it, so that you can make sure that everything is like in a good shape. Okay, and after that you apply your model, and then you have the prediction. So the usability here is medium. Okay, what about the TPOT? The TPOT is a tree-based optimization tool. Okay, and it uses genetic algorithms or genetic programming in general. And simply enough, if you don't know anything about machine learning at all, for example, if you are a physicist but you know how to code, and that's it, you know simple Python, and then you have this TPOT library, then you give it the data as it is. You don't have to do any transformations. You don't have to do any imputations if you have like missing features. It is completely, auto ML thing, auto machine learning. You don't have to optimize anything in the whole pipeline. So the pipeline that we have seen before, I mean, the data preparation, the model selection, the hyperparameter tuning, and the deploying and prediction, and all that stuff. TPOT does it for you, or makes it easier for you. Just grab your cup of coffee and just wait for it to finish the training and the testing and the hyperparameter tuning and everything for you, and that's it. So surprisingly, and I was expecting like at least similar results, but they produced like the same pipeline that we actually tried to implement in the KNN approach. So the final predictor was a KNN, and they only have done like a very simple, how can I say it, a very simple transformation techniques over the dataset, and that's it. So that was automatically done, and at the end, it generates also a Python file that helps you with deploying your model, and that's it. So if you're a physicist and you just understand the idea, but you don't have, or you don't know how to code, or you don't know, for example, like something like scikit-learn or anything, then TPOT is the good thing for you. Then most of the papers that was like talking about the same thing, they used feed for neural networks. So dealing with neural networks is not just like importing TensorFlow or importing Keras, and that's it. That I mean, that's like the best thing. No, you should at least know how many layers you should use, how many neurons in each layer, and what should be like the pre-processing on your data, so that at least the input should be like at least addressable, and it should be easy for the neural network to interpret the input, and also the output itself is very important in this case. I mean, in the ANN case, because of the following. We have a very, very low values for the current. I'm talking about some values of micros, and even lower than micro. So I was afraid that the neural network would, for some situations, to be stuck at some local minima, and that the gradients will be very, very low. So I had to, at least, there is something called TensorPort, and that tool can actually visualize the distribution of the weights over the learning epochs. So I made sure that the distribution is changing by time or over the epochs, and that is a good sign, or a very good sign actually of that. The neural network is able to learn, and the training is going very well. After that, the QNN. It is very hard, actually. It requires you to be very good at machine learning, and also you should at least know the quantum mechanics of the model that you are going to use. So in terms of usability, then it will be very, very hard. But surprisingly, in terms of the complexity itself. And but what I mean by the complexity, I mean the limited number of resources that you're using, then the QNN actually exceeds all of the other models because of the following. I'm using something called continuous variable quantum neural network. It was devised by Maria Scholl, Nathan Keller, and Seth Lloyd, and other great people from the Xanadu team. They introduced it as the following. This architecture actually mimics the same way the neural network or a single unit in a neural network actually works. The single unit is simply enough. You have an input or the x, you have the weight, then you multiply them, and then you add the pi's, and after that you apply a transformation, and then you pass it to the other to the other neuron. The same thing actually happens here. The rotation, squeezing, and rotation. This block here, simply enough, it represents the multiplication process itself. Why does it represent that multiplication process? Perhaps you should read or look at something called the block messiah decomposition and the singular value decomposition of the block messiah. And based on that, you will find that it is simply enough, a multiplication of the input by the weights, and that's it. And this can be generalized. Instead of using simple rotation gates, you can have like a network of interferometers, and you can have like squeezers between those interferometers. So it would be like a sandwiched architecture. And after that, I said that we have to add some pies, and the pies can come from something called a displacement gate. And as the name suggests, it's simply enough. It pushes the values of for example, if the value is 1, then and you want to displace it, then you can either displace it with a positive value or a negative value. And after that, there is something called the nonlinear gate. And let me be very, very specific about this. In quantum mechanics, there's no such thing as like a nonlinear unitary. The only nonlinear unitary that you are going to see is the measurement, and that's it. But in this situation, I mean, for example, like the Kerr gate, or for example, the cubic phase gate, we have higher order Hamiltonians, and based on those Hamiltonians, we can have some nonlinear effects or nonlinear transformation over the state itself. So in the continuous variable model, we have this important thing that we don't actually have in the qubit system. We don't have like a Kerr gate in the qubit system. We don't have like a cubic phase gate in the qubit system. So that is like a good advantage. And then the measurement in the continuous variable model, instead of only measuring zeros and ones, there is something called a homodiode measurement, and that homodiode measurement can produce a continuous output, and that continuous output can actually like theoretically it goes from, for example, like this is like theoretical talking. This is not like the real case, but like very, very high value to that negative value, and that's it. For example, like 5 and -5. So you don't have to devise like some sort of Hamiltonian or some sort of expectation values so that it can scale with your labels. In the paper, or in the continuous variable quantum neural network paper, they said that you can embed your data using the displacement gates. But in my situation, I had two features, and I wanted to use a single Q mode, and like, for example, a single qubit, and that's it. I didn't want to use like many qubits, only a single one. So how can I use two features and encode them inside the Q mode and for a regression problem? So I did the following thing. I used something called displaced squeezed state. And what I mean by displaced squeezed state is that I simply enough scaled the intensity to be between 0 and 0.8. So for example, 0, 0.2, 0.35, 0.5, 0.65, 0.8. Okay, that is the intensity. And the voltage, I have scaled the values to be between 1 and -1. And that's it. And based on that, the displacement values were between 1 and -1, and the intensity were between 0 and 0.8. And based on that, I managed to actually achieve a very comparable performance between the classical neural network were actually around 900 to 1000 parameters. I don't actually remember very well, but it was very, very huge. But the QNN, I only repeated that block 8 times, and we have only 5 features, I mean 5 weights for each gate. So we have only 40 parameters to be optimized. But here we have, in the ANN, we have like around 900 to 1000 parameters. And as you can see, the results are very comparable. And when I made like a very small ANN, like 40 parameters, then in some trials, the ANN had like a very good result. I mean, better result than the QNN. And in some situations, the ANN didn't produce the same good results as the QNN. But the most important thing that I have to mention here is that with a single Q mode, I managed to reproduce the same results of KNN, TPOT, and ANN with a very limited resources. That's the first thing. Second thing is that the convergence rate of the quantum neural network, and even for the continuous variable model, and based on my experimentations with the qubit model, it converges faster than classical algorithms. That is something that that was addressed actually lately in the late of 2020 by a paper about the expressibility of quantum neural networks, or the powerfulness of quantum neural networks, and they used the Fisher matrix to quantize, the power of quantum neural networks. So that is the use case that I wanted to show you. Yes, we can have like lower values of accuracy, but at the end, we used very limited number of resources that for in the case of ANN, it is completely large and it is completely huge. And if I actually have like a good simulator, I mean a good computer that can actually simulate like more Q modes and the time and the resources, I could have managed to create like a bigger QNN, and perhaps I could have like better results. So at the end, I tried to make the comparison between the 4 models in a very specific and in a context way that shows that we have some advantages in the quantum neural network based on its limited resources. And also, if you don't have any experience, then you should actually avoid the way of quantum machine learning and then go to something like TBOT, and that's it. So it depends on your experience, it depends on the resources that you have, and it depends on the way that you would like to process your problem. One final thing that I should also mention here is that in the case of QNN, or I mean, even in the continuous variable model or the qubit model, the current distribution here is extremely low, and that is a problem for any quantum system, because you cannot easily differentiate between 2 similar states. For example, like in this state, like 0.0008 and 0.0010. I mean, this is very close to each other, and a quantum system, like in a real life situation where you would have like probabilities, then this is going to be a hassle. This is going to be a problem. So I had to multiply the current by a factor of 10 to the power of 3, so that I can at least get it a little bit closer to the output of the homodyne measurement. So that is another thing that we should also account for. I mean, the post-processing, when I talked about the pipeline itself, I said that the output should be scaled depending on the response variable that you have, or the target, or the label, whatever you would like to name it. So yes, I mean, this is like the last slide. I mean, the current status of QML. We have a huge problem in the QML community right now, and that problem was also like around, in the last 5 to 8 years, it was present. It is called the vanishing gradient, or parent plateaus. It is the same thing for quantum machine learning. We still have the parent plateaus, and there are a lot of great research papers about handling the way of dealing with parent plateaus and how we can avoid the problem of vanishing gradients. Another thing is that we have two famous variational circuits, the QAOA or quantum approximate optimization algorithm, and the unitary coupled cluster or unitary, yes, I think unitary coupled cluster ansatz. Those are like the, uh, two famous algorithms that can actually be used in optimization problems and chemistry problems. But for some situations, those two algorithms tends to be very huge, and the current quantum hardware does not support, as I have said before, does not support deeper circuits. So we should look at hardware efficient ansatz, and that is the most important thing. You should be careful about choosing your variational circuit at the end. And the final problem that I should mention is that uh, saying that you're a researcher or you know a lot of stuff about machine learning or even quantum machine learning, that doesn't mean that you are like a good person to talk about quantum machine learning itself, or to present new ideas, or even to say that, okay, we have like a huge advantage here. No, this is not the case, and we should be very careful, pay a very careful attention to this problem, because this is bad for us and this is bad for the community, and we should how can I say it? We should regularize the way of our thinking about quantum computing and its effects on machine learning itself, and also the effects of machine learning on the quantum computing community. So please, if you, for example, like find like an article that says that we have like a huge advantage, or you have done like a very simple experiment, and that out of a, out of the blue you get some great results using only quantum algorithm. Do not say that this is like a quantum advantage. Just think about it, and try to look at it like with different angles, different perspectives, because different perspectives will give you like a general overview of your understanding and also of the problem that you are dealing with. So in that way, you will save the community from big scandals. That is the first thing. The second thing, you will enrich the community itself, and you will know that what is wrong with the current status and how we can improve it by thinking a lot, not by just saying we need a lot of money, we need a lot of attention, because a lot of attention in many situations will be very bad. So do not say that we have like a huge thing if you don't know the basics of what you're saying and the reason behind it. So I'm, I'm so sorry for the long talk, but does anyone have any questions?
Right. Thank you very much, Karim. That was very interesting. So don't worry that it was long. So uh, I believe that it was very beneficial to our participants. Yes. So there's one question actually on our chat. I think we've already said that, but let's ask again. Can we use quantum computing for computer vision? If yes, can you suggest some resources and examples, such as notebooks? And are you going to provide notebooks that you have shown in the presentation?
Okay, the first thing, of course, I will give you the presentation, and you can actually attach it to the YouTube video, or you can post it on the group after the talk immediately. I mean, on LinkedIn and Facebook. That is the first thing. The second thing, of course, we can use quantum machine learning in computer vision, in NLP, in speech recognition, in many things. We can do that. Okay, for now, Penny Lane supports the following. You can have like a huge classical neural network, and then you can plug in, instead of like a classical layer, then you can plug in a quantum layer. And based on the way that you would like to do the the computational graph, or for example, you can deal with the quantum layer as a dense layer, and that's it. So the qubits would represent like units in the dense layer, or you can have your quantum layer to convolve around, the input. So you can deal with it as a quantum convolutional layer, or if you have like a single feature vector, you can also convolve around it. So in some NLP situations, you have like an embedding layer, and that embedding layer produces a matrix, and that matrix can then be flattened, and based on that huge feature vector, then we can apply a convolutional layer of 1D dimension, and instead of that classical conv layer of 1D dimension, you can have like a quantum layer, and that quantum layer can actually convolve around, the feature vector. So the same thing can be applied for computer vision and any other application, for example, reinforcement learning. So again, do not worry about, the black box itself, or the model itself. Just think about the input of your problem and the shape of the output, or how you will process the output. And after that, the black box can be easily manipulated in many ways. So do not waste your time on the model itself, but just think about the way that you will deal with the input and the output, because they will facilitate a lot of things for you at the end, and it will make it easier for you and clearer for you why your model actually works or not. So that is the most important thing. But in some situations, to be at least like honest with this, in some situations, introducing a lot of entanglement may not increase the the accuracy. It will only increase the complexity, and it will make the landscape of your cost function to be extremely flat. So it will be very hard for you to train the model. So just pay careful attention to the quantum model itself by the following way. Start simple, I mean like a very simple variational ansatz, and then try to increase its complexity by introducing more layers, or introducing more, qubits, 2-qubit gates or 3-qubit gates, whatever the type of connectivities or entanglement that you would like to introduce, and then compare it on the test data set, and make sure that the test data set is not used for the training phase. Just make sure that you don't have any data leakage in your pipeline.
All right.
Yeah, thanks, Kareem. That was my question. And the other thing is, I mean, is it always the case if I go for quantum computing in case of computer vision, it will give me, I mean, it will save my time, or it time classical computer will be more helpful than the quantum computing?
I'm sorry, are you talking about the time of the training itself?
Yes, I was, see, basically in computer vision, there are, many cases where the processing, I mean, model processing takes a huge time. So my reason of using quantum computing in computer vision is to save that time. So if I can run that model very quickly, that will really help me. So is it always the case, or it is not the case? I mean,
Okay, that is a good question. Okay, so let me answer it in two different ways.
okay.
Up until now, if you want your model to be run very quickly, then and especially in the machine learning case, then use a lot of GPUs and you will be safe. That is the first thing, and that is like an
True.
honest, an honest answer. The second way is the following. For example, if you go to IBM Quantum Experience webpage, and you would like to submit a circuit to be run on a real quantum hardware, then you will find that you will have to wait for like at least 5 to 6 hours, so that for the queue to be finished, and then your turn will come. So if you're talking about using real quantum hardware, then it will be a problem for you. And if you are talking about a simulator, then perhaps if your convolutional neural network is pretty much small and very easy to be trained, then I suggest you the following thing. Perhaps you have heard of it. There's something called QLAX, and it's a qubit simulator, and it is written in C++, but it uses a lot of GPU, and actually it uses the CUDA-NN GPU of NVIDIA. So you can actually check it, and it is only you who can benchmark, the prediction time or the inference time. You can be, I mean, you are the only one to decide this, not me or anyone else. But the training time for you, it will be very cumbersome, and it will take a lot of time to train your whole hybrid model. So I do not recommend, for industrial application or like a direct industrial application, I do not recommend a hybrid model if you want some real-time analysis or real-time prediction. But if you are looking for accuracy, so perhaps if you introduce the quantum layer, or even if you use like a complete quantum model, then it's okay. Then go for it. You should actually go for it if you're not looking for real time. But for now, simulating quantum systems on a classical computer is not that fast. You will need like a very big, supercomputer to simulate very complicated quantum systems. That is my only answer. But if you have like a real quantum hardware besides you, and you have the full control over it, then perhaps it will be faster for you. I don't know the complexity of the quantum circuit that you are trying to do, but in any way, perhaps it will be faster. Another thing that you should also think about is what type of hardware are you targeting? For example, the qubit gate is very fast for executing the gates. So the gate time is very small. I mean, I'm talking nanoseconds here. But if you are dealing with the ion traps, then the gate time is in the order of milliseconds. So again, I don't know if you want like real-time analysis or not. So there is a huge difference between acting with milliseconds and acting with nanoseconds. So again, it depends a lot on the final product. So again, always think about the machine learning pipeline. I have a business problem, and that business problem should be like addressed properly. And based on that address or that addressing, you should carefully choose the algorithm, the embedding way, and the deployment way. A lot of things should be taken into account. So always think of it as a business problem, and based on that, at least you will find some clear or innovative ways to include a quantum part and the classical part. Why not?
Okay, got it. Thanks.
You're welcome.
Okay, thank you, Karim. So maybe one more question that is a bit relevant. Can we somehow formally mathematically prove that some
Can you what? I'm sorry?
Can you hear me now?
Yeah.
Okay. So the question is, can we formally mathematically prove that in some cases quantum computers can really give a speed up comparing to GPUs, for example, or comparing to classical algorithms for machine learning?
Okay.
Are there any formal proofs? Are you aware of some formal proofs?
Formal proofs. Based on in my honest and humble opinion, and based on my understanding, and please also triple check what I'm saying here. We can calculate inner products using quantum circuits easily, using something called the Hadamard test or the SWOT. The SWOT test. Okay, and calculating the inner products is very fast using the qubit system. So and it also perhaps we can have like fewer how can I say it fewer runtimes or fewer circuit executions. And based on that, we can calculate the kernel matrix or the gray matrix using a quantum computer perhaps faster or even as fast as like a classical computer. So that is something that we can do. And there are a lot of literature talking about swap test and how we can use it to calculate the inner product. That is the first thing. The second thing, introducing, feature maps and the inverse of the feature map is very, it is very achievable on the current quantum hardware. So I think that calculating for this specific case, I think that quantum computers, at least if it didn't give you the best accuracy, then it will compute it for you very, very fast. I mean, theoretically very fast, but I'm not sure of, if you are waiting in a queue and you are waiting for the output to come to you like in an API request or any of these other things. I'm talking right now, like generally speaking, about the whole pipeline and the whole software pipeline. Then I don't know if it will be fast or not. If you have like a dedicated quantum computer for you, perhaps it will be fast. So talking about the mathematics, the inner products can be calculated efficiently on a quantum hardware, and it can be fast. Even it can be faster than a classical computer.
All right. Okay, thank you. I think we don't have more time for questions now, but yeah, that was a great talk. So thank you very much, Kareem, once again. If anyone is interested, I see that Przemek has already posted a link to our Google Forms. So if anyone would like to obtain a certificate, then please fill it in. And yeah, maybe just some final words. So let me just share my screen once again.
Okay.
All right. Can you see my screen again?
Yeah, I can see it.
Okay, perfect. Yeah, so I just wanted to let you know that our next meeting will be most likely on 19th of April. So there will be announcements at the beginning of April, hopefully. And yeah, we would like to thank once again our strategic partners and honorary patrons for supporting us. And if you are interested, then of course, let's stay in touch. Please follow our Facebook, Twitter, LinkedIn profiles, or join our mailing list. And we hope to see you next time in April. So thank you once again. Have a good evening. Have a good week. Thank you, Kareem. I will stop sharing my slides now and
You're
stop
welcome.
recording.